So welcome back. Last week we discussed two main topics. First of all, we look at all the difficulties that enter in the paradigmatically hard problem of simulating macromolecular complexes. We joked on the fact that you can say if you can make it here, you can make it anywhere, meaning it's kind of conspiration of complicancies. Starting from the fact that we don't know the force field, actually starting from the fact that we don't even know whether we can use a force field, as we shall see today, or when we can use a force field, or where we are forced to use bona fide Schrödinger equation dynamics, which is horrible beyond just a couple of degrees of freedom, right? So, but then even if you can rely to classical approximation, we run into all sorts of problems, the decoupling of time scales, the presence of high barriers, which might be entropically driven, or so that require large exploration to be overcome. The fact that the energy landscape is intrinsically corrugated, meaning that even small conformational transitions have to overcome small barriers. So in other words, there is dynamics at all scales, which makes diffusion extremely slow. And in addition to that, even if we were able to solve that, we have a problem the system is high dimensional. So once we have generated a fair amount of statistics, how do we extract any meaningful information out of it? Right. So all of these problems will be at the heart of this course. But in the second lecture, we focused on a specific problem. Now, the way we entered that problem was somehow detached from the molecular framework. But now we can embed it into the molecular framework in the following way. Suppose that in order to integrate the dynamics, we need to run very short time steps, as we shall see today, right? But at those very short time scales, some of the dynamics might be quantum. Now, how come that by summing up many classical approximations that you shouldn't be doing, because the dynamics is intrinsically quantum, how come that by summing up many wrong answers, you get the right answer in a long time? This is a fairly fundamental question, right? I find no discussion of it in all the books that I checked, which makes me very angry. And the reason is that the answer behind it is kind of subtle. The answer behind it is the fact that the details of the long-time, long-distance physics, the details of the short-time, short-distance physics are irrelevant to describe the long-time, long-distance physics. And we gave a proof of that during our discussion on the renormalization of the Schrödinger equation. Remember? And what did we find? We found that even without knowing what was the potential at very short distances, even assuming something that had no theoretical ground at that as mere delta function, remember? We were actually able to reproduce very nicely the soft energy levels, the energy levels associated to states where the wave function was very broad. And the reason for this was if the wave function is very much spread around, the part of the interaction we don't know is a hard short distance core, remember? And we don't need to know the details of the short distance physics to influence the large distance physics. All we need to do is a couple of effective parameters that implicitly encode the short distance physics we have no control over. Okay? The second point that we came to conclude was, now everything that we used to get that was basically a Fourier analysis of the part of the physics that we didn't know, and only keeping the part that was relevant at low momentum, so large distances, right? But that means that as long as we get the Fourier components right, all we need to guess is the right Fourier modes, right? which means that even if we don't do the two different models that have the same Fourier components, we're giving the same physics, right? Now, of course, two different models will not have all the same Fourier components, otherwise they would be the same model, right? They can have, up to certain accuracy, the same first components, or very similar first components. This is the analogy that we made with a multiple expansion. Imagine we have two charge distributions that to very high accuracy give you the same monopole, so the same total charge, and large enough distance, you cannot distinguish between them. Okay? Why? Because all the details of the short distance physics gets renormalized into some effective parameters, the charge in this case. Okay? Now, the same happens with the force field. We don't need to know very well the short distance physics as long as we're interested in the long distance physics. We can make a guess, which is equivalent to the delta function, but could be any guess, and fit the parameter. And as long as this is short distance is very separated from long distance, assumption number one, and it captures the right symmetry, right overall properties, assumption number two, then we should be able to use it to describe the long distance physics. So even if our description of the short time dynamics is wrong, if there is a decoupling between short and time, we might still be able to recover the right long time dynamics from it. Okay? Okay, this was more or less the summary of the last two lectures. And from today, we sort of start from the scratch, the course, in the sense that with this deep piece of information rooted in our mind, now what we want to do is we want to lie down the foundation of molecular simulations, starting from the very fundamental level and building approximation one on top of the other, so that we really see, as theoreticians, as this molecular dynamics follows down from first principles, and what approximations are being made at each step. Okay? So let me just mention foundation of molecular mechanics, M&M. Okay? And of course, where do we start? If you were to write the most fundamental theory for a macromolecular system, what would be your starting point? I mean, it's nothing creative, it's the very trivial answer. What are molecules made of? Yes, but you don't know the forces between atoms, right? So you cannot start with an atomic description, because then you will need the forces between the atoms, which is precisely what we don't know. Let's make one step. Let's go one step up until we find something we completely know. At some point, we're going to stop because we know the standard model, right? So somewhere in between molecular mechanics and Higgs boson, lies the answer, right? So let me ask the next question. What are molecules, macromolecules, made of, if not atoms? Because that's too coarse-grained. No, I'm going the other direction, because I want things. Macromolecules make cells or make whatever tissue you want, but going the other direction, going macroscopic. What are macromolecules made of? Atom, okay. One step further. No, monomer is in the other direction. Macromolecules are made of atoms. Monomers, if you want, are somewhere in between, because they're made by many atoms, and many monomers make a macromolecule, right? So they're somewhere in here. But I'm asking you, since the force between atoms are not controlled, we need to go further in more macroscopic. What's the next step? Electrons and nuclear. Do I need nuclear physics? Do I need proton and neutrons? Who says yes? Who says no? Guys, I'm not eating you. I'm here to discuss with you and learn by talking. Physics is learned here.
You can approximate like 1/r, just a simple potential.
Why?
Because the 1/r approximation.
No, there's another reason. Why don't we need atomic nuclei to study macromolecules? Why don't we need to solve the nuclear physics of protons and neutrons? Because it's short distance. And the details of the short distance physics are not relevant to study the long distance physics. We can just say there's a nucleus with a certain mass and a certain charge. These are my two effective parameters, all I care about. Okay? So, the Hamiltonian, so what I need to do is the Schrödinger equation for electrons and nuclei, right? So what I need to do, so here is electrons, and let me call big capital N stands for nuclei, and we will distinguish between neutral, okay, fine, nuclei. Will have a charge, of course, that depends on the nucleus, okay? Okay, so what is our theory? We will define R to be the collection of all electrons' positions, the electronic coordinates, okay? And capital R, the collections of nuclear coordinates. You with me? Okay. Then my next step is to write down a Hamiltonian for the Schrödinger equation, right? Remember, I promised you that I would start from the very foundation up. So the Schrödinger equation would be minus sum 1 over number of nuclei in the system of h bar squared over 2n I, so the nuclei, gradient with respect to the i's, right? Negative sum over I going from 1 to number of electrons in the systems, h bar squared divided by 2 mass of the electron, which I will not label, I will write as just small m, but the small m with the label is the nuclear mass. Okay? Let me use a capital letter to remind myself that the nuclear masses are larger than the electron mass. And then I have the gradient over the small i's coordinates. And then what do I have? I have the Coulomb interaction between all the nuclei, right? I'm writing this in a schematic form. This would be the sum of all pairs of products of charges divided by by distance, right? The Coulomb force. Of course, I have the Coulomb interactions between all the electrons, and then I have the Coulomb interaction which couples electrons and nuclei. And all the dynamics of my macromolecules is written down in a beautiful Schrödinger equation, which depends on the r's, on the small r, time, and it's given by the Schrödinger equation. R, capital R. Beautiful to write, completely useless if you want to do biophysics. But let's stop here. Well, I'll wait for you to write. Now, while you write, if you guys have questions and things that should be, or you feel should be straightforward, or you have the impression that I think should be straightforward, but they are not, stop me. I don't care. There is no stupid question whatsoever. Okay? The only stupid question you can make is the one that you don't ask. Okay? because remains in you, and boop. And if you accumulate sufficiently many unanswered questions, you lose enthusiasm in physics, believe me. Enthusiasm is reinforced by the feeling of understanding. So the more you say, okay, I shouldn't ask this, I leave it there, and then these things, they accumulate, and then eventually you say, okay, why should I care? Let's forget that. Let's keep things under control, okay? Fine. Does this make sense to you? Now I immediately make a question. Why not spin? Why didn't I write and spin? Think about it. Is spin interaction is spin important, to describe macromolecules? Well, it is if you want to build a wave function according to the Pauli principle. Of course it is. So I am assuming that within this wave function I'm already accounting for antisymmetry of the wave functions, blah, 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 things that you don't need to worry in this course, okay? But my question is magnetics interaction due to spin, forces, why don't I put them there? Any question, any idea? Well, because magnetic interactions are relativistic. In fact, you need the Dirac equation to get them out properly. What is the typical momentum of an electron in an atom? Is it relativistic or not? Well, you might start thinking, putting down, it would be a nice exercise and show computing that p squared c squared is much smaller than m squared c fourth, right? But you already know the answer because you studied atomic physics and there was no spin there when you did the hydrogen atom. Right? Well, there was if you want to do the hyperfine splitting of the atoms. You go back to your structural matter course. These are very, very tiny interactions that give you the splitting between energy levels. But these are they are called hyperfine because they are very, very, very small. And since we're after macromolecular systems, we don't have the luxury to worry about the details, okay? So let's forget this physics. Beautiful. We have a fantastic theory. Now we know everything. We know the Hamiltonian, and we know the equation of motion. We even have a scale, the atomic scale. Let's go. And then you're stuck. There's nothing you can do. Well, you can do if you have maybe one electron and a proton, and you look at scattering, maybe you can make it. Maybe a handful of electrons with extremely sophisticated, possibly AI-driven, quantum computing-driven in the future systems, you can deal with dynamics of quantum particles as long as they are a handful. As soon as you go to moderate number, quantum dynamics is an impossible task. All right? So, beautiful but useless. But that's where physics starts. Physics starts when you find two scales, and you can put one on top of the other to form a parameter that is dimensionless and much smaller or much larger than one, so that you can start neglecting things and keeping others, right? So what are two scales that are widely separated here? Two dimensionful quantities that are very different from one another. Well, H bar is everywhere, forget about that, right? The charge is everywhere, come on. Yes, huh? In what? Maybe you said it, but I didn't hear it. What is different between nuclei and electrons? The mass. Here are the two parameters, 1 and 2. Well, yes. Why do I hesitate? Well, because there are hydrogens around in macromolecules, but hydrogens are made by one proton. Well, at least the proton is 2,000 times heavier than the electron, right? That should be good enough. So the first parameter expansion we can make in the entire course would be alpha mass of the electron divided by mass of the nuclei much smaller than 1. Actually, it's 10 to the minus 3 or more, because you say oxygen is dozen of atoms, roughly speaking, so order 10 to the 1, so that would be 10 to the minus 4, and so on and so forth. You never really need any heavy element. But anyway, that's the first parameter. So now we know that everywhere we see 1 over m big M, relative to small m, we can neglect, correct? And this is not something that only enters in macromolecular system. This is physics. Physics always works this way, neglects something and keeps something else. Okay. So, in order to capitalize on this, I make an ansatz and I write my Schrödinger equation, which depends on the small coordinate and the big coordinate. I define it to be in the following way. This is an ansatz. I'm splitting a part that depends only on the radial coordinates times something that depends on both. By the way, I can always do that. I mean, the worst comes to the worst, this becomes 1, and this will give me this, right? So I made no approximation as long as I don't specify what these guys are. Now, what do I do with it? What do I do with it? I write down my Schrödinger equation, which I will write in the following way. The kinetic energy of the heavy coordinates, okay, operator, which is the gradient there, the Laplacian squared of the kinetic energy, plus the kinetic energy of the electrons, plus the entire potential from now. And instead of writing the time-dependent Schrödinger equation, which eventually I should need, right? Let me just write the time-independent Schrödinger equation, because if I know all the spectrum, you know that you can reconstruct the full solution from the static solution. Since we're not going to go over all the spectrum anyway, let me not carry around derivatives over time, okay? So this is equal to, well, this goes to phi times r equals some energy levels, phi times, sorry, kappa now. Right? I've done nothing. I've plugged this into the static Schrödinger equation. Okay? Now here comes the beauty. This is the wave functions that depends both on the electrons and on the heavy coordinates. This depends only on the heavy coordinates. Right? You follow me, guys? It's not difficult. In an scale from 1 to 10, where do we place this? I turn my head so I don't know who's talking. Come on. Huh? Come on, guys. Let's. 8? In terms of difficulties? Okay. I have to. Okay.
No. Understanding.
Okay. Phew. No. I was already imagining how to restructure the course. Okay. So now you see what I mean here. When the heavy kinetic energy acts on this wave function, I neglect this term. This acting on this, because it would be much smaller than this acting on this. Okay? So the electronic kinetic energy will be large. Okay? And the nuclear kinetic energy of this wave function will be smaller. So it's like adding a peanut on top of a pile of food, like in Monty Python movie. Have you seen the Monty Python movie where the guy blows up? It's a guy that eats too much, and eventually he's a huge guy, and it's called The Meaning of Life. It's a beautiful movie. If you have a good guts, you can see it. So the guy eats too much, and the attendant wants to make him blow up because he's fed up by the fact he eats too much. So he offers a small mind and says, I cannot take it anymore. Come on, just a small mind. So eventually he accepts the mind and he blows up. So it never happens this way. Usually the small corrections don't bring to catastrophes, right? So now adding the kinetic energy is the mind, and this is the bite of food that you have already had, the kinetic energy of the electrons. Okay? So you can neglect this when applied to this. But you have to keep it when you apply to the purely nuclear wave function because you don't have anything else to compare to. You see what I mean? You can neglect the nuclear kinetic energy, denominator, because in the numerator you can put the electronic kinetic contribution to the same quantity. They add up when they act on this. But since this only depends on the nuclear coordinates, there is no such a thing as relative contribution. I need the kinetic energy on the nuclear coordinates. Okay? So I cannot neglect it. There's nothing else otherwise. Okay? Fine. So if you do, simplifications occur. They are dramatic. This is called, by the way, the Born-Oppenheimer approximation. So within the Born-Oppenheimer approximation, Bohr, what do I get? I get that the previous Schrödinger equation here splits into two. Because there will be a part that only involves the R's and the other. So in other words, within the Born atomic, let's do it. Let's do it. T electron, which acts on the small r, on phi and chi, plus T plus T nuclei that acts on phi and chi, plus V that acts on phi and chi, right? I've just applied the Hamiltonian. And this is equal to energy times phi and chi. Now remember, the next step is, this is nuclear. Does this depend on the electron coordinates? Are the nuclei wave function? No, I can take it out. Derivative, right? What about here? Well, here, I can do one more thing, if you think about it. The kinetic energy, when acting on the part of the wave function, is smaller than this kinetic energy when acting on this part of the wave function. So, now I take this out and neglect that. Okay? But then, now I look at this wave function. Let's look at this part. If I collect this, I get chi T electric on phi plus V that acts on both, right? Chi and phi. So I can put the phi here and the chi out. It's a multiplicative thing, right? The potential multiplies the wave function, so I can always do that. Okay, so here I see the structure of the Hamiltonian of the electronic variables, But in this potential here, the nuclei are fixed, right? Because this depends parametrically on R and on small r. Yes?
I didn't get why the y can be brought out.
Here it's multiplied.
Okay, yes, but with v does not
V, okay, so let's make an example. And let's say v of x is equal, say I have v of x of y, okay, a two-dimensional potential. And it multiplies a wave function that depends of both x and y. And a part of the wave function that depends only on y. Okay, maybe this is, I don't know, x squared plus y squared, or whatever it is, even if they don't sum. Let's put an exponent and divide it by sine of the square in unit of pi. I don't really care what all this is over. But this multiplies that. Okay? So whatever this number is, I can always bring this here, right? It's a number. Whatever it is, it's not a derivative that I cannot put it across. It's a diagonal operator in position representation, technically speaking. I can do whatever I want. So if I do that, the chi comes across and I can collect it from the left and I get the Hamiltonian of this. You see it? Okay, so this suggests that I should do the following. I should first nail down my nuclei with a knife to fixed position. Solve this problem with the nuclei fixed and looking at the energies. Replace this by the eigenfunction, and then go back to the equation. Okay? So what do I do? So what do? I say, okay, first, solve T electron plus V on the phi, which depends on the R's, and parametrically on the nuclear positions. This depends on both. Equals some energy. Since I fixed my nuclei, the energy will depend on how I nail down the nuclei, right? I change the nuclei, I change the energy, because I get a different Schrodinger equation, correct? If I change the position of the nuclei, my potential here will change. For instance, I can put two nuclei too close together and the energy will blow, right? So the energy then will change, right? So this energy will depend on the position coordinates of the nuclei. And this will multiply phi r. Okay. Write down and think. What have we done? Now, I could do things at basically any level of formalism. I choose now for the next step to stick on the relatively low level of formalism, because otherwise it becomes an atomic physics course, okay? So what have we done? We were interested in dynamics, remember, dynamics. But I wrote a static Schrodinger equation. Now, if you have a static Schrodinger equation and you have all the energy levels, remember, you can still get dynamics. How? By summing every energy level. Remember, x of t is equal to the sum over all the energy levels into the negative I over h bar en t phi n, right? But these are the solution of the static Schrodinger equation. Now, low level of details. But we are in a system which has a lot of degrees of freedom and environment. And so energies trying to dissipate to the ground state. In fact, if you do optics, you know. You excite optically your sample, you see a signal, but if you stop exciting, your signal will go down after a while. That's collapsing to the ground state. Now, but how long does it take? You see, if the time of collapse of my wave function would be comparable with the dynamics of my system, I should see the superposition of all these waves into the dynamics. Correct? And I have to do things thoroughly quantum. Right? So how long do we expect an electron to take to relax to the ground state? That's the question, right? Because that's the question that will tell us whether we can neglect all the excited states or we can just stick to the ground state. So, okay, what do you expect? We learn to do physics here, first of all. In physics, my supervisor in PhD always say, you are a physicist if you can estimate everything. You're not a physicist if you cannot make estimates of things arbitrarily. So let's do estimates. How long will it take to an electron to relax? What would you do? And I insist we do this together because when you will analyze your molecular simulations, even if it will not be about electrons, you will have to estimate things. So I insist we learn to estimate. Okay? So, ideas. How long does an electron take to relax? Scale, I don't need a number, right? I don't need a precise number. Why?
Because the energy between the levels is on the electron volt.
Very good. That's very good. So delta E, roughly speaking, H bar, right? Now delta E is in the electron volt, which means delta T is in the H bar over delta E, which is femtoseconds. Great. And it's not by, now we start seeing what I meant by wrong answer. We integrate classical dynamics with femtosecond time scales. Not to mention quantum dynamics in the ground state. Here we're talking about excited states quantum dynamics. That should be on the femtosecond scale. So super wrong. We are making two approximations, one on top of the other, if we use Newton's equation of the femtosecond scale, right? Fine. Okay, so, but I'm not interested in the physics at the femtosecond scale, not even a picosecond scale, as we shall see. I'm interested in the physics at the nanosecond beyond, hopefully millisecond and seconds if we are very good, right? So forget about femtosecond. That means that the femtosecond is a long time scale for me, as long as I'm interested in quantum dynamics. So the time scales that I'm interested in are much longer than the femtosecond, right? Which means that for any relevant time interval I'm going to look, the thermalization to the ground state happens in a snapshot, right? It's an instantaneous effect. So I don't need all of those phases and stuff. I need to stick with the ground state, basically. Which means that the dephasing happens very, very soon. The system collapses to the ground state, and basically electrons are almost instantaneously in the ground state. So this is the cow effect. What is a cow effect? No, it doesn't have this name. I call it this so it sticks to your memory. If you go into the countryside, you see a cow. It is usually full of mosquitoes and travels very slowly. So slowly that for the mosquitoes, it's no problem to adapt and be always around the cow on the same distribution, roughly speaking. Right? This is because the time of motion the mosquito have is so much faster, they relax immediately to the equilibrium distribution around the cow. Right? Very good. So, not only I could always go to the static as long as I keep all of these energy levels, but I don't need to keep all of these energy levels because the system relaxes to the ground state. I only need the ground state. The lowest energy level. So, what did we learn? We learned that the heart of the problem that we stumbled so far is evaluating the static Schrödinger equation for the electrons at fixed nuclear positions to get the ground state. Right? And unfortunately, I'm not done with it because this corresponds only to one fixed nuclear position. Right? But before we say what do we do with this, let me just say that this is called the electronic problem. And it's the paradigmatic quantum chemistry problem. Of course, quantum chemistry can do more than just the electronic problem. But the electronic problem is one of the hard, that the quantum chemists, hard problems that quantum chemists lose their nights for, right? Okay, so there are many methods to solve this. We will use none of them for reasons that will become clear in a moment, because even using them would be too hard for most applications. But let me just say, we could, in principle, solve this problem. Let's assume we have very large computational power. Let's say infinite computational power. Not infinite, because if I had infinite, I would solve the Schrödinger equation. But almost infinite, okay? So I can solve this, and it takes me nothing. Maybe I have trained a super complex neural network that solves the equation for me. And instead of solving the Schrödinger equation, it basically interpolates on billions of solutions that he has seen. And so I just have to call the network, it will give me a solution. That's a kind of situation that is not so far from present. Okay, when I talk about revolutions going on in the AI era, right? So suppose we can do that. What do we do with this? Well, we can plug this back here, and in here, instead of this, we can plug the corresponding ground state, because you see it's chi t, here, instead of this, I can plug ER, E naught R, and the phi naught of R given R. The corresponding solution, the ground state energy, will depend on the positions. So if you do that, this part and this part will go away, and they will become chi times. Okay, let me write it down, not to become too messy. After I plug in the solution for the ground state, I come up with a new Schrödinger equation. This time, I have the kinetic energy of the nuclei acting on the wave function of the nuclei times this E naught, which depends on the nuclei, is equal to the total energy times chi.
Why the phi in the other cases becomes phi naught?
The phi becomes phi naught because I assume that I don't need all the spectrum. All I need is the ground state.
Yeah, but like in the term phi tr.
So I erased the equation, unfortunately, but let me recover it. We have T E key phi, right? Plus T nuclei chi phi plus V chi phi equals E total chi phi. I'm using E total because the E that we will use in a moment. So now the electronic kinetic energy, so chi can go through, we already discussed it, right? Here I neglect sorry. I neglect, yes. So I get chi t phi. Here I get plus phi t and chi because I neglect the nuclear kinetic energy when applied to this that contains both. Remember? Plus I have phi chi phi equals E total chi phi. Now, this T phi chi V phi, this I can replace with E naught of R phi naught. Everywhere I can put phi naught, in fact, because system collapses to the ground state very soon. So all I need is a phi naught, right? So if I do that, instead of these two terms, I get chi E naught phi naught, and this depends on R, right? The energy depends on the nuclear position. And then you see, everywhere phi cancels now. You see? So 1, 2, 3. So now I'm left with a new equation, which is a Schrödinger equation, in which I don't have a potential, but I have an energy that depends on coordinates. Okay? Because remember, this energy depended on coordinates. So this is a new Schrödinger equation where the potential is the ground state energy at that fixed position. Okay? So, first of all, does it make sense? Of course it makes sense, because, see, what is the energy of a system? Energy of a system is the electron, is kinetic energy plus potential energy, right? But if my system is very slow, what dominates is the potential energy. So basically, this is telling me that if the electrons are very fast compared to protons, a nuclei are very slow, everything goes if what the electrons see are heavy chaos nuclei, they collapse to the ground state. But what the nuclei see is a ground state distribution of electrons around that depends on their position, right? The cow sees mosquitoes everywhere, around itself, not in another place. And if it moves a little bit, the position of the mosquitoes changes. And if he flaps a tail, the mosquitoes follow the tail. So the position of the mosquitoes depends on the position of the cow. So clearly, the energy here is the energy on the nuclei due to the effect of all the other electrons in the system. So this is called an effective energy or an emergent energy, an emergent potential, because it's not microscopic, it's the result of putting all the others. Okay? But now, it means that basically the role of the Hamiltonian for the nuclei is not played by the potential, but by the ground state of the electrons. Okay? So what I can do is to rewrite my original dynamical equations in the following form. Let's see if you follow me. We started off with negative I h bar d by dt psi of r and r equals h of psi r and r, and we replaced it with two equations. One is the Hamiltonian for the electrons. For only the electrons, a fixed nuclear position is equal to the energy of the electrons at that fixed nuclear position. for the ground state, right? The one that we derived before. And now we know that this is the potential that governs the nuclear motion, right? So what we can do, if we want to understand dynamics, I can write the Schrödinger equation for the nuclei only. So now I have to use another word because chi is in fact a wave function, a static wave function. So let me call it psi, the wave function for the nuclei depending on time. And this is equal to the kinetic energy plus E naught of the nuclei plus E naught that depends on R times the psi. You see, what it's telling me here is that if I want to study the dynamics of electrons and nucleus, Schrödinger equation, I first have to solve for the ground state of the electrons. The ground state of the electrons will give me the ground state energy. I interpret this as the effective energy of the nuclei in that nuclear configuration, plug it into a Schrödinger equation as if it was a potential. And the result will give me formally the dynamics of the nuclei. Correct? Other questions? I made a long premise to arrive to here because now we can learn about you can learn about applications to biophysics already at this level, at least at the level of terminology. So I did not do that because I'm a frustrated theoretical physicist that needs to spit out formulas. Otherwise, he feels sick, which I am, but that's not the only reason I'm doing this. Okay? Other questions so far? Call me if the meter for impossibility to digest passed 5, so to say. Okay? In that case, we have a problem. Okay, so you might say, hey, but that's cheating. Not cheating, but that's useless. It's a typical theoretical physicist, useless kind of mumble jungling. You do formulas, they're beautiful, but what do I do with that? I started with one equation, and now I have two equations, one of which is as difficult as the other one, is the Schrödinger equation with time. Why am I doing all this? Getting more difficult equation out of one equation. Because sometimes solving, if you have to climb the stairs, you'd rather do 3 small steps than 1 big step. Okay? So, this is impossible. But the electronic problem is actually manageable. Okay? The electronic problem is manageable. Not always, but with density functional theory approximation for many problems of interest, at least for small peptides, or not for maybe not for even peptide, but for amino acid level, pairs of amino acids, or molecules that are, say, 40, 50, 100 atoms. That's still manageable. Okay? Okay, so if you get to this point, let's assume you can do this. For small molecules. Then you can plug it in, and there are far fewer nuclei than there are electrons. Plus, nuclei have this fantastic thing. They are distinguishable if they are different quantum number. For instance, if you have an oxygen and a nitrogen, they are not indistinguishable. They could be even bosons, but when they're fermions, they are distinguishable. So you don't have to worry about spin statistics, the antisymmetry of the wave function, because they are distinguishable particles in many cases. So solving this is just another scale. So when you do actually this, and you solve for the electron, for the nuclei with dynamics quantum mechanically, you are said to do ab initio molecular dynamics. The word ab initio that you might hear sometimes refers to the fact that you don't have a model, a heuristic model for the energies. You evaluated the brute force by solving the electronic problem on the fly. Mr. Carr and Mr. Parinello, two very, very famous Italians, invented the Carr-Parinello approach, which is a way of doing that very efficiently, solving the ab initio problem very efficiently. But there are other methods, of course. But this is a really fundamental problem. Like, when do we need ab initio? When, first of all, if suppose we're interested in dynamics where the quantum nature of nuclear motion is important. For instance, if I'm looking at processes where the quantization of energy levels of vibration of nuclear are relevant, and we'll see when this could be in a moment, clearly I cannot go with a classical calculation because that would not give me quantization. I should at least do semi-classical, but say quantum calculations, okay? You with me? But there is a more important, so as biophysicists, you might not be interested in that unless you really want to do spectroscopy, maybe Raman spectroscopy done very, very well, and blah, 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 okay? But on the other hand, if you want to study an enzyme, in an enzyme, the action of an enzyme is basically inducing a chemical reaction, right? In a chemical reaction, the protons, the heck they stay in the same, the nuclei and the protons and nuclei, they actually do weird things. They wave function restructures completely. And there's no way you can hope to describe that by assigning the nuclei a fixed, and the protons and neutrons in the nuclei a fixed location. You have to do things quantum mechanically, putting protons and neutrons there and see whatever happens. Or putting atoms there and see how they move and they bind differently, depending on what level of detail you want. If you have a protonation or if you have a chemical bond that breaks, right? So ab initio is important whenever quantum transformation of the atomic species take place, and therefore in principle to study enzyme activity, and that's why a good deal of quantum chemistry deals with enzymatic activity. Okay? So building up, we start to see first processes that we might encounter as biophysicists. Say phosphorylation, just to come up with a name that I've been using lately. Okay? Okay, but what if we don't have to do that? What if I just want to do protein folding? Who cares about chemical reactions for now? Well, clearly, solving this equation is now shooting a mosquito with an atomic bomb. Because the nuclei become classical pretty soon. How soon? Estimate. When does a nucleus, how long does it take a nucleus to get classical? How classical is a nucleus? And I give it to you, this is more difficult. A nucleus in thermal equilibrium at temperature T. Does it move classically or quantum mechanically? Right? That's the problem. So, let me formulate the question. Is thermal motion of nuclei classical? That's the big question, which again, I would love to see discussed in books. More. Some books do. But let's do this thoroughly. So what kind of nuclear motion are we talking about? Well, we can in principle talk about bonded motion, but we'll deal with that in a moment. So vibrations, for instance, and ask if it's classic or not. But that's already at least a two-body force, right? Two-body system. Let's take one step further, one step less. Let's take one single nucleus flowing around in a thermal bath. Right? How do we know if it's reasonable to treat it as a particle diffusing, say, with a Brownian motion? As we will do for 99.9% of this course. Well, I'll give you a hint, okay? You want, so your nuclear will have a wave function if it's quantum, and this wave function will be spread. It will be spread by an amount that is roughly 1 over p. It's momentum, correct? The spread of the wave function should be not too large compared to the nuclear size. Otherwise, the nucleus is bona fide delocalized, right? I am delocalized, but I'm delocalized on a scale that you don't see because I'm much larger than that delocalization wave function. Gazillions of orders of magnitudes, right? But if I was an electron, my wave function would be delocalized over regions that are large, or the electron is point-like, as far as we know. That's not a good example, but the nitrogen has a final radius of about 10 to the minus meters, 10 to the minus. How many meters is a size of an atom? 10 to the minus 10, aka the angstrom. So the spreading of the wave function of the proton, let's take a proton, okay? How does it compare to the radius A naught, the Bohr radius, which is roughly speaking 10 to the minus 10 meters? Okay? That's an interesting question. Well, delta x is roughly speaking h bar over delta p. Okay? But now, you must say, oh, that's the Broglie's wavelength. Remember that? The Broglie's, noi lo chiamiamo the Broglie. But in the American speaking, they call the Broglie's, but it's the Broglie wavelength. Okay? Yes, but what's the de Broglie wavelength? Depends on momentum. But now, I know what is the typical momentum of a particle in a thermal bath. What is it? How do I estimate the typical momentum of a particle in a thermal bath? Estimate. Ideas?
kb times k.
Wow, right. We know that the average kinetic energy of a single particle, right, is 3½ kT, 1/2 kT per degrees of freedom. So the typical square momentum is 2m kT times 3½ And since I'm interested in estimates and not in precise values, 3½ equal 1, as far as I'm concerned. Okay? Okay, so root. So that the delta x is all the order of h bar divided by the root of 2 times the mass times kT. Okay. We know everything, right? We know h bar, we know the mass, we know kT. Now what we need is a consistent set of units, not to get crazy, right? I would like you to do the exercise and not me to do it. You come with the answer next week, okay? Find a consistent set of units. Use the one that Gromax uses, for instance. So we all use the same one. So you go, look for Gromax, look for the manual. See, in the beginning of the manual, they will tell you, I'm using this set of units. H bar is in picoseconds, kilojoule per mole. Mass is in atomic mass units. And you notice as long as you express those units consistently, you can be safe. You don't want to use the value for C in meters and the values for mass in grams, because then things don't make sense anymore, right? So I'd like you to estimate this for next time for a proton and for an oxygen. And you'll discover that even though there's a root of m here, So first of all, a proton will be, roughly speaking, 10 times lighter than an oxygen. It's 16, forget it, 10. Okay? Root of 10 is 3. So you are 3 times more classical with oxygen than with proton, even though the mass is much larger. Okay? You follow me? Which means that in principle, so what you will learn? You will learn that even in the simplest possible problem, nuclear are fairly classical, but hydrogens, 30% corrections. You get, if you do the calculation properly, or if I'm not mistaken, I've done this calculation last time many years ago, that the spreading is of the order of a third of the Armstrong for the hydrogen. And it's 3 times smaller, so a tenth of the Armstrong for an oxygen. So 10% corrections, who cares? We are after much bigger effects. 30% corrections, yes, still, we do it, but, you know, not very happy. Okay? Let's do another estimate. Let's talk about atomic vibration, say bond vibrations. What is the typical frequency of a bond vibration? Order of magnitude. Do you know? If you're a biophysicist, you should. That's I'm insisting because I want you to get into this mind, not because I'm trying to demoralize anyone. We need to know scales. Knowing equipments, knowing experiments is important, but knowing the scales of the underlying system is extremely important. So, typical, let's say I will be a little bit cavalier, because I'm after very rough estimates, basic estimates. But let's say the typical frequencies, so these are the pulsations, which is smaller than the frequencies. But let's say the typical pulsation of harmonic oscillators that you can use to describe atomic bonds are in the order of picoseconds to the -1. Of course, they are softer and harder, and you can go into any kind of problem, okay? So this is 2 pi, so this is 2 pi ni, if you want. And ni is actually, 2 pi is almost 10, is more than 10, so it's not exactly, it's already 1 order of magnitude there. But let's forget. So now what do we want? What are the typical discretization level of this? What is the size of the quantization level in a harmonic vibration, given the frequency? H bar omega, right? So my typical quantization effect would be of the order of H bar omega, right? Now, here the lesson is almost finished. I don't have time to go into a discussion for this. Let me just jump ahead with the answer. Is this large or is this small? It depends compared to what? You need 2 scales. So what is the scale you want to compare to? Energy scale. What is the relevant energy scale for any system in statistical physics? Big hint. Any system is in statistical physics. There's only one thing. KT. Right? So how does this compare to KT? For 300 Kelvin, of course. Now, exercise. You plug in picoseconds to the -1, and you see whether you are in this regime that you have an harmonic oscillator with many tiny discretization levels, and KT, the fluctuations are all the KT. So it's like when you go and pay for your pizza, you don't care that the quantization of euros is 1 cent, because the price of the pizza is always in euros, never in cents, right? But if you go and buy, I don't know, whatever is 1 euro cent anymore, but whatever. If you want to buy a single whatever, and it's 30 cents, and you start to worry, right? So if the temperature is much larger than the quantization level, you don't care. If the temperature is comparable to the quantization level, then you should care. Well, it turns out that the energy is comparable to the quantization energy, to the quantization energy is comparable to the temperature for atomic vibrations, bomb vibration. You shouldn't do any classical approximation. Why can you do it? Because I'm interested in the dynamics in the long time, long-distance regimes, and whatever happens in the short time, long-distance regime, I don't really care about the details. I only care about the implicit effect along scales. So I can close my eyes to the fact that the system is actually quantum at those scales, pretend it's classical, and solve its classical equations of motion, as long as the following conditions apply. Number one, I'm not interested in chemical reactions. There's no classical limit of a chemical reaction. Okay? Number two, I'm not interested in photoexcitations or anything like this, of course. This goes without saying. Okay? Number three, I'm interested in the long time regime, long distance regime. But then I can replace this beautiful equation here with a Newton's equation. Mi Ri double dot acceleration is equal to negative gradient of E naught of R right? Goal old beloved Newton's equation. So, if I knew the electronic positions, the electronic energies for any fixed position, I could insert it into the Newton's equation. Of course, the Newton equation step, integration step would be much faster than the time it would take me to solve the corresponding new Schrödinger equation, because I would have to solve it almost every time. Okay? Almost, because maybe you can get along with some tricks to do it just occasionally, but still have to do it many, many, many times. So, this is the foundation of molecular mechanics. However, it's still quantum if you have to solve for this. Molecular mechanics comes from getting heuristic force, assuming you know this E of R without having to solve every time the Schrödinger equation. So, in other words, this guy here, gradient of E naught R, has a dimension of a force. It enters a Newton's equation, so it should. So, negative gradient with respect to R of E at R is called the force field. So either you know the force field because somebody gave it to you, which means that he has estimated before, or he has come out with some trick to get it, or he's done something to get it. Or you compute it from underlying Schrödinger equation if you are extremely powerful. Once you have the force field, you solve the Newton's equation. So what people do and call molecular mechanics or molecular dynamics, the words interchange sometimes, is solving a Newton's equation with a classical force field. Now, finally we understand what we're talking about. Many things we still don't understand. First of all, where does temperature come in these equations? Proteins have a temperature. There's no temperature here. We have to figure out how to bring that information in, right? So this is not the end of the story. Now, but it's the beginning of statistical physics. The good news is no more quantum dynamics from here on in this course. Bona fide quantum dynamics. We will use mathematics of quantum mechanics sometimes because make things easier. But real quantum mechanics is over. So when you go on your simulation platform, GROMACS, OpenMM, Amber, Amber is a force field, but you see what I mean, maybe Charm and blah, 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 right? You can select the force field. There's one, have you ever done any molecular simulations? You will in this course. But at some point you are asking, what force fields do you want to do? Well, there's an industry of people that infer this force field using everything they can possibly can. They use some quantum mechanical calculation of some systems, but quantum mechanical calculations are only approximate, and they don't work very well when you propagate them to large systems. So you have to make assumptions, and so they use them to fit functional forms. We'll discuss the force field next time, but basically you get functional forms that you guess out of physical-chemical intuition. For example, let me give you an example. The electronic charge will be distributed somehow, but given the electronegativity of certain atoms, it will be more closely packed around some atoms that become locally negative, right? And less close to some other atoms that will become locally positive, right? So all of a sudden, the electronic distribution will generate a Coulombic attraction between two atoms. So what people do, they guess one term in this. They will take E of R is a functional form with many, many contributions. One of them would be an effective Coulomb interactions where the effective charges of the nuclei appear. Okay? You see this? These effective charges are the same as the monopoles. They are effective parameters that parameterize and underline short distance physics we don't want to deal with. Are the C0, C1s, and C2s of the exercise of the Schrödinger equation. Okay? So, in this lecture, we have learned what force fields are. We have laid down the foundation of molecular dynamics. We have an idea of where it's supposed to hold, what it's supposed not to be able to describe. But we have a reassuring argument based on renormalization group that tells us that, okay, we should not do this, but as long as we are not going into put our nose precisely in that corner where quantum mechanics should be used, which is the picoseconds or the femtoseconds time scales, for instance, and we stick far from that and only look at global motion of a peptide, we shouldn't be too worried, provided we can get a good estimates on this. Which is a little bit like putting the dust under the carpet. Because what is a good estimate for E of R? Is there a real good estimate? Is it possible to guess a function that has all the symmetries that we need, all the ingredients, to generate all the Fourier modes that are relevant at low momentum? Nobody really knows, right? So what people do, they try, so far, heuristic way, many, many different functions, and compare to experiments. And they say, hey, I have these fantastic force fields. It predicts the ground state of proteins beautifully. How do I know? Because if I run a microsecond long molecular dynamics simulation from the correct native state, it stays there. And if I run it from a state that I made up, it starts to go somewhere else. Okay? Fine, fantastic. Let's use it. Okay, I'll use it to study intrinsically disordered protein. And while my colleague has fantastic results and publishes on Nature, I get shitty results because the same force fields doesn't work for intrinsically disordered protein. Why? Because the chemistry of an open chain is different, and the quantum mechanics of an open chain may be different from that of a closed chain because you interact more with water, because the environment is different. So in principle, you have to design your force field to match that particular value, that particular problem. In the ideal world, we would go around with just one force field for everything. But in the real world, it doesn't work that way so far. Then people go and say, okay, let me try RNA. Now, RNA is a charged polymer. A lot of electrostatics there. The quantum chemistry of electrostatics with a lot of charges around is far more complex. Is it still possible to use the same functional forms that people have used for proteins? Maybe not. In fact, RNA and DNA force fields do not perform as well. They're much less known because there's much less experimental data available. So people are working on building that. And here comes the most important application of all if you want to make money. Getting small molecule protein target interaction. So you can sell yourself and your soul like I did to pharmas. Okay? Force field for small molecule protein interaction are yet another chapter. And guess what? They are barely known. Why? Because why there is about 100,000 structures in the database to fit your parameters with, in the PDB database. There's much less structure available for protein drug interaction, and big pharmas, whenever they generate some, they keep it. Why should they give it away? Of course, I mean, you have invested millions and millions and millions. I don't think that Google gives all of his technology away for free, right? So everybody there is some available knowledge, there is some unavailable knowledge. And I would like to close this lecture to say, at the beginning of the first lecture, I say we want to study this in 2025 plus. Meaning doing things that wasn't possible to do 15 years ago. Now there is a big industry of people trying to do precisely what I told you before. They are making huge progress in using emerging technology to solve the electronic problems. In particular, training neural network as interpolators. You provide a neural network with a lot of Schrödinger equation calculations, very precise, and you try to train a network to learn the underlying E of R. And maybe you cross-link it with experimental information if you have it. And you try to make hybrid learning schemes where you combine theoretical aspects and experimental aspects into large networks with attention layers that look at something particular. And I hope I'm not talking Arabic to you. The attention layer is an architect where you're able to sort of redirect the attention of the neural network to learn from certain specific environments, variable, and blah, 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 and combine this information with the rest. So you can do things much more elaborately than just feed-forward neural network, which is what you can find if you type neural network 101 on YouTube, okay? But all this technology has a very, very natural application in getting the force field. Whoever will get the most precise force field will break the bank in all sense, academically, commercially, okay? That's one point. The other point is, of course, trying to use quantum computers, which can do very well quantum dynamics, because basically quantum circuits are implementation of quantum dynamics, because there are operators that change the state of the qubits in time. And you try to build your gates, these operators that change the state of your qubits, to represent what the Schrödinger equation does with the time evolution operator of the Schrödinger equation does to your wave function, so that you get the time evolution of the wave function. I'm simplifying a hugely complicated business here, of course, right? But I just want to give you a grasp of where we are at the edge of breakthroughs in many directions. I'm not sure we are at the edge of breakthrough for quantum dynamics of electrons. Not because quantum computers are not promising. I personally think eventually they will be promising in many applications. But for this specific application, we need incredible accuracy for making quantum chemists happy, because chemical reactions, it's a really, they even have a name, chemical accuracy, to mention very large accuracy. It's more likely that quantum computers for dynamics will be used to study nuclear reactions, where a few percent error is still an acceptable error. But maybe I would be proven wrong, and I'd be very happy to be proven wrong, of course. Okay? So I hope I gave you a first overview on this. Next time, we start to open the Pandora vase question. Where is temperature in here? Where is statistical physics? This is an isolated system. How do we integrate that for real? Not just, writing an equation is one thing. Solving an equation is another. So we will start from the simplest algorithm to solve that equation. But we immediately face the problem that it doesn't have a temperature built in. So what do I do if I want to know that my system is at 300K? So and how do I fix the pressure? I know I'm in 1 atmosphere, right? So this would be next 1/2 lectures. Grazie e buon fine settimana.